In this video, we introduce a very important algebraic object called an ideal. We're going to talk about the relationship between ideals and affine varieties. So we'll start by reviewing some of the main concepts from sections 1.1 through 1.3 in the Ideals, Varieties, and Algorithms text by Cox, Little, and O'Shea. Then we will provide a definition for ideals. We'll talk about the ideal generated by S polynomial functions, and then we will talk about the interpretation of that ideal. We'll state the Hilbert basis theorem. We won't justify it yet. We're going to get to that later, but we'll just state it. And then we will talk about proposition 4, which is that affine varieties are determined by ideals, not equations. So let's start with our brief review of sections 1.1 through 1.3. In 1.1, we learned about fields. We reviewed the field properties. Basically, a field is just a set of objects where you can add, subtract, multiply, and divide in all the ways that you're familiar with and comfortable with real numbers and complex numbers. We talked about notation for polynomial functions. We talked about a field K. We talked about this notation for polynomial functions. And this would be a representation of a polynomial in a polynomial ring with coefficients in the field K in the variables x sub 1 through x sub n. And then we talked about n-dimensional affine space. And that's just a set of ordered n-tuples where each of the values in the n-tuple is from the field K. And then after all of that, we defined what was called an affine variety. So an affine variety is usually represented by V. We say V of f sub 1 through f sub s. And this is a subset of n-dimensional affine space. And here we're thinking of these functions, or these polynomial functions, f sub 1 through f sub s, from this polynomial ring in the variables x sub 1 through x sub n with coefficients in the field K. Now remember what this is. This affine variety V is a solution set to a system of polynomial equations. And it's a solution set in K, an n-dimensional affine space. I said n polynomial equations, I was wrong. S polynomial equations. The affine variety defined by the polynomials f sub 1 through f sub s is the solution set of this system of polynomial equations. So we'll have f sub 1 of a sub 1 through a sub n, or x sub 1 through x sub n, excuse me, equals 0, and f sub 2 of x sub 1 through x sub n equals 0, and eventually f sub s of x sub 1 through x sub n equals 0. So this is a set of ordered n-tuples in n-dimensional affine space so that all of these polynomial functions are equal to 0 at the same time. And we saw some examples of affine varieties whenever you're talking about solution sets of systems of polynomial equations like this. You might have a finite number of points, or you might have curves or surfaces or higher dimensional objects. And we saw that conics, polynomials, quadric surfaces, intersections of surfaces, all of those were affine varieties. And I believe that was basically what 1.2 was about. And then we said that if we have two affine varieties, V and W, So if we've got one variety defined by the polynomials f sub 1 through f sub s, and another variety defined by the polynomials g sub 1 through g sub t, then we were able to show that the intersection of v with w, that's the solution set of a system of polynomial equations that looks like this, and a system of polynomial equations that looks like this, where the functions are g sub 1 through g sub t. The set of all points that belongs to both of those is also an affine variety, and it's the variety defined by the polynomial functions f sub 1 through f sub s and the polynomial functions g sub 1 through g sub t. We were also able to show that the union of those two varieties is also an affine variety. To find the polynomials that define this affine variety, you just take the polynomials of the first variety and the polynomials of the second variety, you multiply them together for I between 1 and s and j between 1 and t. You have all of those products. And those are also polynomials, because a polynomial times a polynomial is a polynomial. So if we have two polynomials, or excuse me, two affine varieties, we can take finite intersections, or we can take their intersection and we get an affine variety. We can take their union and we get an affine variety. And that works for no matter how many affine varieties we're starting with. So what we showed here was that finite intersections, so that is intersections of a finite number of varieties, and unions, it's unions of a finite number of varieties. And those are also affine varieties. Remember what an affine variety is. Sometimes we're talking about these algebraic objects. It's really a very simple principle. It's just a solution set, an n-dimensional affine space of a system of a certain number of polynomial equations. So after we learned about affine varieties and their finite intersections and unions, we learned about parametric representations of affine varieties. We called this representation the implicit representation of an affine variety. Implicit representation is useful for us if we want to determine if x sub 1 through x sub n, or a sub 1 through a sub n, is a solution to the system of equations, or alternatively, if we want to think of a sub 1 through a sub n, we want to think of that ordered n tuple as a member of this affine variety, an element of this solution set. Then we just plug in that ordered n tuple over here. If we get 0 for all the equations, then we know that that number, or excuse me, that ordered n tuple belongs to this set. Now there's also another representation which is really useful, and that's what we discussed in the last section in 1.3, and that was the parametric representation of affine varieties. And because we're interested in systems of polynomial equations and systems of equations involving rational functions, we were particularly interested in the rational parametric representation of an affine variety. And basically what this allows us to do is it allows us to describe all of the points, or most of the points in the affine variety. And because it allows us to describe the points, they're also pretty easy to graph when you're using a computer. So if we have an affine variety that looks like this, where f sub 1 through f sub s are polynomials in this polynomial ring with coefficients in k in variables x sub 1 through x sub n. The solution set is a subset of n-dimensional affine space. So one way that we can write this rational parametric representation of an affine variety, or one parametric representation rather, is to have x1 equal to some rational function in the variables t sub 1 through t sub m, x2 equal to a different rational function in the variables t sub 1 through t sub m, and so on. Eventually we get to x sub n, because remember the solution set is a set of ordered n tuples. So we have a description for each variable x sub 1 through x sub n. And these are functions of m variables, t sub 1 through t sub m. And these are all rational functions. So the r sub I belong to this, it's not a polynomial ring, it is a field. Rational functions, the set of rational functions in t sub 1 through t sub m with coefficients in k is a field. So these are all rational functions in this particular field. If you're saying to yourself, why would I want a rational parametric representation or a polynomial representation? Why is that particularly important as opposed to using, say, sine and cosine for a circle, or a constant times sine plus a constant times, or a constant times sine for one of the components and a constant times cosine for a different one for an ellipse, and so on. You might think, why would I be interested in rational and polynomial equations? The reason that we're interested in that is because the theory is so rich. Like, we know a lot about this polynomial ring, and we know a lot about this field of rational functions. So it's helpful to be able to talk about solutions in these forms because we know something about the sets that these functions here come from and that these functions over here come from. And then we looked at a number of examples and we saw a couple of applications. One was in robotics, which showed that the state of a robotic arm can be described as an affine variety. And then we also talked about the Bezier curves, which allow us to create just a wide variety of beautiful curves by controlling a number of points, like the initial point, the terminal point, and the tangent vectors at the initial and terminal points, and then sort of piecing those together to create a smooth curve if that's what we want. So that was all of that. Now we're going to tie that into the next topic. It's one of the most important topics, if not the most important topic in all of algebraic geometry. We know what affine varieties are. Those are very closely related to an object called an ideal. So this is definition 1 in section 1.4. Now, initially, it's just going to seem like a bunch of rules. It's going to seem pretty abstract, but it actually has a meaning, as we'll see. We're going to call a subset I of the polynomial ring in variables x sub 1 through x sub n with coefficients in k. And we're going to call that an ideal. If it satisfies the following. So first, the zero polynomial has to be a member of I. And if f and g are both members of the ideal, then the sum of f and g must be members of the ideal. And then third, if f is an element of the ideal and h is any element in the polynomial ring, so it's any polynomial, and that polynomial does not have to be in the ideal. then if you take the element in the ideal and you multiply it by that polynomial that's not in the ideal, that's in the ideal. So if there is a set I that satisfies all of these, so 0 is in the set, for any two elements in the set, their sum is in the set. For any element in the set, if you take it and multiply by a polynomial that may or may not be in the set, that's still in the set. That is called an ideal. Now, if you're trying to determine whether something is an ideal, you just need to check these three conditions. Initially, this might not seem like it's very important. It's very abstract, and you might think it's not particularly meaningful. It's very rich. It's very meaningful. But you sort of have to get used to the technical details and what this says first in order to really understand what it means. So that is the definition of an ideal. We're going to look at a particular example next, and then we're going to show that that example satisfies these three requirements. And then we're going to talk about what that particular ideal represents and how that's related to affine varieties. So here's a definition. Let's let f sub 1 through f sub s be polynomials in the polynomial ring with coefficients in the field K. Then you're going to define this notation in this way. This symbol here is the sum, as I goes from 1 through s, of h sub I times f sub I, where h sub I through, or h sub 1, h sub 2, h sub 3, all the way through h sub s are just any old polynomial in the polynomial ring over here. So that's the definition. So for particular functions f sub 1 through s sub s, if I wanted to, I could expand this. This would be h1 times f1 plus h2 times f2 plus h3 times f3 all the way through h sub s times f sub s. This represents this set where you just take polynomials h sub I from our polynomial ring. You multiply them by the polynomials over here and you add them together. Now it turns out that that's an ideal. This is level number 3. It says that if f sub 1 through f sub s are in that polynomial ring, then this set is an ideal of the polynomial ring. And then we call that set the ideal generated by f sub 1 through f sub s. Now we're still talking in abstractions. We haven't talked about what this means yet, but we know it's kind of like a linear combination of polynomials, but instead of multiplying by constants, we're multiplying by other polynomials. The claim is that this is an ideal. So let's prove that it's an ideal. And to prove that this is an ideal, all we need to do is check that those three conditions are satisfied. First, it needs to be a subset of this polynomial ring, and it is, because we know if we take polynomials in our ring and we multiply them by other polynomials in the ring and add them together, we're still in the ring. So we've got this subset of our polynomial ring. We know that it's an ideal if 0 is an element of that set, if the sum of any two elements of the set is also in the set, and any element in the set multiplied by an element that's just in the ring, any polynomial that's in the ring is also in the set. So clearly, this is a subset of our polynomial ring. Because if the h sub I are in the ring and the f sub I are in the ring, then when we multiply them together and add them, then we're still in the ring. It's because of the properties of rings, we know that sum has to be in this ring. Okay, now the next thing that we want to do is we want to check that the first condition is satisfied. Well, 0 has to be an element of that set. And we know that 0 is an element of this set because every element of this set has this form where the h sub I are just polynomials in the polynomial ring. Well, we know that every polynomial ring has a 0 polynomial. So we can let h sub I equal 0 for I equals 1 through s. And we would get this. Obviously, if I take every function on this list, I multiply it by 0 and I add them together, I get 0. So 0 is definitely a member of this set. Now, the second thing we need to check is that if f is in this set and g is in this set, then their sum is in that set. Well, by definition, if f and g are in this set, they can each be written in this form. So we can say that f can be written in this way. It's the sum as I goes from 1 through s of p sub I times the f sub I. And then similarly, g is the sum as I goes from 1 through s of q sub I times the f sub I. And this is where the p sub I and the q sub I are in our polynomial ring. Now I'm using different letters, but don't let that bother you. These are just polynomials, just like the h's are. So we're using p's here and q's here rather than using h's. Well, if I've got this polynomial and I'm adding them together, well, the sums start and end at the same place, so we can write that as a single sum. And then, of course, we could factor out the f sub I. Now, since p sub I and q sub I are in this polynomial ring, when I add p sub I and q sub I together for I equals 1 through s, well, the sum has to be in the polynomial ring. And since that sum is in the polynomial ring, then this is just equal to some h of I times f sub I. And then we can see, because it's in this form, we've got all of our f's from this list being multiplied by polynomials from the polynomial ring and added together. So if f plus g are in this set, then, or if f and g are in this set, then f plus g is also in this set, because this has that form up there. So we have just shown that f plus g is in this set here. Now I'm not 100% sure about what I've written here. I said let f and g be a member of this set, then by definition f is equal to this and g is equal to this, where these two guys are in the polynomial ring. Okay, therefore when I add these together, that sum plus that sum can be written as a single sum. We can factor out the f sub I. We can say that that is the same as that. Since these guys are in the ring, then the sum is in the ring. That sum can be denoted by h sub I. And so you've got a polynomial in the ring times the f sub I, and you add those together, and that's equal to f plus g. So f plus g must be a member of this set. Okay, and then the last thing that we want to check is this. This last one says that if f is any element of this set and h is any polynomial, you can take that polynomial and multiply by that polynomial f from the original set, and it's going to be in the set. So we're just going to let h be a polynomial, just any generic polynomial. Then h times f, where f is given by this expression here, is h times this sum. Now we can distribute that polynomial over addition. So you can bring that h inside. And you can regroup like that. And so what that tells us is that h times f can be written this way. Since p sub I was a polynomial, h times p sub I is still a polynomial. So we've got polynomials times the f sub I, and we're adding them together. So h times f is a member of this set. We've got too many commas there. Okay, so we have a zero element if f and g are in the set, f plus g is in the set, and if h is in the polynomial ring, then h times any member of the set is also in the set. So all three of the requirements of an ideal are satisfied. So this set, which again can be written like this, or if you prefer, you can expand it like this. That set is an ideal. Let's say I equals 1 through s. Of course, we're assuming I is a whole number between 1 and s. Okay, so that's easy. Easy little proof, easy little exercise. Now, if you're like most students, you're probably wondering, what does it mean? Like, what is the significance of this? Why should we care? There is actually a really great interpretation. And if you think of some concrete examples probably that you've seen in pre-calculus or college algebra, or in anytime you were solving systems of linear equations or systems of nonlinear equations, or if you're in calculus 3 and you're solving systems of polynomial equations because you're optimizing a function of several variables, all of this is about to make a lot more sense when we make it concrete. So let's think about this interpretation. Okay, Since we have these functions f sub 1 through f sub s, which are in this polynomial ring, I'm sorry I keep saying that word polynomial ring over and over again, but we're going to be talking about rings a lot. So we have these guys right here. Well, we can relate these polynomials to a system of equations where all of the equations are equal to 0. So these polynomials can be related to this system of equations. And of course, the solution set of that system of equations is an affine variety. But once you have this system of equations, these are not the only equations that you have. If you've ever taken an algebra class, if you have, just for example, 2x plus 4y equals 0, and a negative x plus 5y equals 3, well, if I have those two equations, I can use those to derive other equations. We often use these equations to derive other equations that make it easier for us to solve this system of equations. So one of the things that we might do is we might take this second equation and multiply it by 2. Leave the first equation alone. I guess we could have divided the first equation. That's okay, we'll just take the second equation and multiply it by 2. So I'm doubling that, I'm doubling the 5, I'm doubling the 3. If I then add these together, I get 14y equals 6. And then if I divide both sides by 14, well, that's 3 times 2 over 7 times 2. I get y equals 7, or 3 over 7. So the fact that y equals 3 over 7, that stemmed from the fact that this equation was true and this equation was true, and this equation was true. The fact that this equation was true stemmed from the fact that this equation was true. We were able to take this system of two equations and two unknowns and change it into another system of two equations and two unknowns. And then we were able to add those together and able to come up with one equation and one unknown, which we were able to solve for y. We were able to find out that y would have to equal 3 over 7. And if we know what y is, we can use y in this first equation or the second equation to find out what x is. So there are equations that follow from other equations, and that's something that you're very comfortable with and that you've done many times before. So we're going to think about that same idea just in a little bit of a more abstract way. If I have S polynomial equations like this, we could use these equations to derive other equations. So if I wanted to, I could take this equation and multiply by a generic polynomial, and this equation and multiply by a polynomial, and this equation and multiply by a polynomial, and then we could add all of those together, and that equation would also equal 0, because if I take both sides and multiply by h1 here, and both sides and multiply by h2 here, and both sides and multiply by h sub s here, well, h sub I times 0 is always going to give me a 0. So if I have this system of equations, I also have a whole bunch of other equations. And those other equations look like this. H sub 1 times f sub 1 plus h sub 2 times f sub 2 plus h sub 3 times f sub 3, all the way through h sub s times f sub s. And since I'm multiplying both sides by those h's, and h sub I times 0 is 0, when I add these guys together, I'm going to get this. Notice that this is the polynomial over here in this ideal generated by the polynomial functions f sub 1 through f sub s. And this is almost as generic as possible, because we can take any polynomials, h sub 1 through h sub s, in this polynomial ring, multiply them by the functions that we have, the polynomials that we're setting equal to 0, and then add all of those together, and we're still going to get 0. Now, if you're saying to yourself, well, sometimes they're not 0, just remember you could move that 3 to the other side, and you could set all of these equal to 0 if you wanted to. So with that in mind, what we have is this is a generic consequence, or this equation is a generic consequence of the original system of equations. And that system of equations comes from taking all of the polynomials in this set and setting them equal to 0. And the solution set of that system of equations would be an affine variety. So I hope you can see now why ideals are important, or at least this ideal generated by the polynomials f sub 1 through f sub s. The ideal isn't the s polynomial equations you started with. The ideal consists of all of the polynomial equations that you could get by manipulating these equations and getting other equations. Just like we did with this. When I took this and I multiplied by 2 and then I added these together and I got a new equation, I could have gotten a lot of different equations. I could have taken this one and multiplied by 1/2 and then added them together to get rid of the x's. I could take this one and multiply by 1,000,000 and take that one and multiply by -x and add them together, and that would be a consequence. So we could take this and multiply it by a polynomial, and this multiply by a polynomial, add them together, and that would be a polynomial consequence of this original system of 2 equations with 2 unknowns. Now, when we multiply by polynomials here, we're usually multiplying by polynomials with a purpose. We're trying to get rid of one variable at a time so that eventually we can find the solutions to this system. We're going to talk about finding solutions to this system in the next couple of chapters. But all of that's going to be related to this idea of an ideal. So the ideal, again, is not the original system of polynomial equations. It's not even just the set of polynomial equations that define the affine variety. It's all of the consequences of this system of equations. It's all of the polynomials that would result from taking the polynomials that you have, multiplying them by any old polynomial that we have in the ring, and then adding them together. So the ideal is every possible consequence of this system of equations. So let's write that down. So that's cool. That's much cooler than saying that, oh, 0 has to be an element of the set, and if f is in the set and g is in the set, then f plus g is in the set. If h is in the ring and f is in the set, then h times f is in the set. All of that's important, but it's meaningful. And I hope that you get excited about the meaning. Like when I realized that that was the meaning, I was like, oh my goodness, this is a really awesome geometric object. So the ideal generated by the polynomials f sub 1 through f sub s, that's this, which can be written this way. The textbook author, says that this is the set of all polynomial consequences of the original system of equations. And that's pretty cool. Now, when I first read that sentence, it was intriguing, but I was still like, what do you mean polynomial consequences? Again, this is what we mean. If we have polynomials f sub 1 through f sub s, we can think of them as corresponding to a system of S polynomial equations. So we can define this system of S polynomial equations in n unknowns, and those n unknowns are generally denoted by x sub 1 through x sub n. If we take each of those polynomial equations, we multiply them by a generic polynomial in our ring of polynomials and add them together, we're going to get a new polynomial. We want to think about all of the possible ways we could do that. That's what this ideal is. So if we multiply all the equations by polynomials and we add them together, we obtain a polynomial consequence or an equation involving a polynomial. That is a consequence of the original system. Now, the ideal is actually a set of polynomials because it's a set of all polynomials that you can get by taking these polynomials, multiplying them by polynomials, and then adding them together. But if we take those polynomials and set them equal to 0, we get the polynomial consequences of this system of equations. So I'm going to say this is a set of polynomials consisting of all polynomials that would equal 0 if f sub 1 through f sub s were all equal to 0. And that's powerful. That's much more powerful than just saying that these two equations have to be true. What that's saying is that if these two equations are true, there are infinitely many other equations that are also true. That ideal consists of all of those polynomials that you would set equal to 0 to get a resulting true statement, the consequence of these equations being true. Okay, and now I think you can see how ideals are going to relate to affine varieties, because affine varieties are the solution sets of these. So let's write that down. So the affine variety, typically denoted by V, of f sub 1 through f sub s. So this is the affine variety defined by f sub 1 through f sub s. This is the solution set of that system of equations. So here I have a set of polynomials that I've set equal to 0. The solution set of that system of equations is a subset of n-dimensional affine space. We call that an affine variety. And the ideal is not that list of S polynomials, but it's all of the polynomials that would equal 0 if you took every single possible combination of these polynomials multiplied by polynomials in the polynomial ring and then added together that would still equal 0 because these guys equal 0. So the affine variety is defined by the polynomials and the ideal is defined by the polynomials, but the ideal is a set of polynomials that result from these equations being true, and the affine variety is a subset of n-dimensional affine space where these equations are all true. I hope that helps. So I would focus on those words. This is a set of polynomials consisting of all the polynomial consequences of this system of equations, or the set of polynomials that would equal 0 if all of these were 0. And the affine variety is the set in n-dimensional space where all of those polynomials are equal to 0 at the same time. Okay, so let's practice this with an example. This is exercise 1. In section 1.4. It says consider the equations x squared plus y squared minus 1 equals 0 and x times y minus 1 equals 0. This system of equations describes the intersection of a circle and a hyperbola, which we can see. If I graph this top equation, that's equivalent to x squared plus y squared equals 1. So we know that that's a circle of radius 1 centered at the origin. And then over here, I could solve for xy if I wanted to, or I could solve for y if I'm okay with x not being equal to 0, add 1 to both sides and then divide by x, and we get y equals 1 over x, which is a hyperbola. And it looks roughly like this. I think it crosses at 2 places, or 4 places, we'll see. This actually kind of reminds me of baseball. Now, part A of this exercise asks us to just use algebra to eliminate y from the equations. So we know that y is equal to 1 over x. We can substitute that into the first equation. So we have x squared plus y squared equals 1. And y is 1 over x. So if you want, you could square the numerator and square the denominator. And if you don't like the fractions, you could take this entire left-hand side and multiply it by x squared to clear the fractions. That's legal as long as you do the same thing on the other side. So we've got x to the 4th plus x squared times 1 over x is just 1 equals x squared. So we end up with this. Oops. Subtract the x squared from both sides and you get this. So we've eliminated y from the equations. So now we have this. This is a polynomial consequence of these two equations being true. If this is true and this is true, then we're guaranteed that x to the 4th minus x squared plus 1 is also equal to 0. Now I'd like to show this a different way. I'd like to show that you can get x to the 4th minus x squared plus 1 as a sum of these two polynomials multiplied by other polynomials in the polynomial ring of, let's use this one, the polynomial ring with coefficients in their real numbers and two variables, x and y. We want to take these guys, multiply them by h sub 1 and h sub 2, add them together, and show that we can get this from these. So we say that this is a polynomial consequence of this. So that means that this x to the fourth minus x squared plus 1 is a member of the ideal generated by these two polynomials. That's the claim. And if that's true, that means that x to the fourth minus x squared plus 1 is equal to some function h sub 1 of x and y times this first function. I'll call that my f sub 1, and I'll call that my f sub 2, plus a different polynomial function of x and y times my second function, f sub 2. So the question becomes, I'm so sorry, excuse me. What two polynomials would we have to multiply these polynomials by so that when we add them together, we get x to the fourth minus x squared plus 1? It's kind of like going back here. When we wanted to eliminate x, we multiplied by 2 and we added them together. When I wanted to eliminate y, it was a little bit harder to just eliminate y from this form. So we solved this equation for y and substituted. We used that method. But this time I want to do something different. I want to ask myself, what polynomial can I multiply this by so that when I multiply this one by a polynomial and I add them together, all the y's are gone and I'm left with x to the fourth minus x squared plus 1. And we were actually given a hint, so we're going to follow the hint. The hint says, multiply the second equation by x, y plus 1. And I think that that makes sense. When I look at this x, y minus 1, I know that I might have some simplification if I multiply by its conjugate, x, y plus 1. So that's what they're suggesting for us. I think it's a good idea. So we've got x squared plus y squared minus 1 equals 0. We're going to leave that one alone. And then we're going to take xy minus 1, and we're going to multiply by the polynomial xy plus 1 on both sides. Xy plus 1 times 0 is 0. So these are equivalent to this. We've got x squared plus y squared minus 1 is our first equation. Down here, if we multiply first times first, it's going to give us x squared y squared minus 1 equals 0. Still, what to do from here? Well, I guess we could take this second equation and we could solve it for y squared by adding 1 to both sides and dividing by x squared. And then we could substitute, and then we would end up right here in exactly the same place that we were before. But I don't want to do that. My goal is to multiply this equation by something so that I get rid of all of the x's, or excuse me, all of the y's. Because remember, our goal is to eliminate y's from the equations. Well, they gave us this hint. They told us to do this, and now we're here. And I've got an x squared times y squared here. Well, I could get rid of that x squared times y squared if I multiplied this first equation by negative x squared. And then I would have a negative x squared y squared and a positive x squared y squared, and I'd add them together and the y's would be gone. And I bet I would be very close to this equation. And actually, let's see if I do that. I actually don't want that. I want a positive x to the fourth. If I multiply this one by negative x squared, I'm going to have a negative x to the fourth. So let's just keep this one. Let's take this one and multiply by a positive x squared. And then let's take this one and just multiply it by -1 and see what we get. So now I have x squared plus y squared minus 1 equals 0. And when I multiply that by x squared, I have x squared times x squared, which is x to the 4th, plus x squared y squared minus x squared equals 0 times x squared. And then down here we had x squared y squared minus 1 equals 0. And we're going to multiply that one by -1. So we'll have negative x squared y squared minus a -1 is +1. And then we have the opposite of 0, which is 0, of course. So then when we add these guys together, that's great. We get x to the 4th minus x squared plus 1 equals 0, which is exactly the same polynomial consequence that we came up with over here. Now, if you're saying to yourself, so what? It's okay. It's not particularly exciting that we were able to get from here to here. But I just want you to know that this is one of infinitely many polynomial consequences. If this is equal to 0 and this is equal to 0, every possible combination of these is a consequence of the fact that both of these are equal to 0 at the same time. So if this is 0 and this is 0, this times this plus this times this is going to equal 0 for every h1 and h2 in this polynomial ring with coefficients in the real number system. All of those would be satisfied, and I'm not 100% sure about those pictures. Okay, so now the question becomes, well, what was h1 and h2? Like, what did we actually multiply the first equation by? And what did we multiply the second equation by in order to get this over here? Well, let's walk through it. We started with our original equations, and then we took the second equation and we multiplied it by xy plus 1. And then after that, we took the second equation and we multiplied it by -1. So what we really want to do is we want to take this xy minus 1 and we want to multiply it by an xy plus 1 and a -1. Okay, so we can do that. And then we say, well, what did we do to this one? Well, we multiplied that by positive x squared and then we added them together. So the claim is that x to the 4th minus x squared plus 1 is equal to h1 f1 plus h2 f2, where h1 is x squared and f1 was that x squared plus y squared minus 1. And h2 was -1 times the quantity xy, was it plus 1 or minus 1? So whatever that sign was, it was the opposite. This was xy minus 1. This is xy plus 1. So this is our f1 is in red, the f2 is in red, the h1 and h2, which are just any old polynomial from our polynomial ring, are in black there. And if you simplify this, you can see that we've got x to the 4th plus x squared y squared minus x squared minus, and then when you distribute here, you have a difference of squares, x squared y squared minus 1, distribute the negative. And then these guys reduce, and ta-da, you get the same thing that we had on the other side. So this is just one of many polynomial consequences of the fact that this and this equals 0. There are infinitely many consequences of the fact that this is equal to 0 and this is equal to 0. One of the consequences of both of these being 0 is that this polynomial is also 0. We could have just as easily eliminated x rather than y. We could have gone in a different direction. We could have chosen not to eliminate either of the variables, and we could have multiplied by all kinds of things to write this in different forms. But all of those would be elements of the ideal generated by this polynomial function and this polynomial function. So remember, this is the set of all functions, all polynomials, h1 times x squared plus y squared minus 1 plus h2 times xy minus 1, where h1 and h2 are in the polynomial ring. that we're interested in. And it looks like I've written it this way. It's as generic as possible, but it looks like our coefficients are real numbers, and we don't have x sub 1 through x sub n. N is equal to 2. So we're not going to call those variables x1 and x2. We're just going to call them x and y. Okay, so that was our example. That was an example from the exercises. At this point, we have reviewed affine varieties. We talked about finite unions and intersections of affine varieties. We talked about parametric representations of affine varieties. And then we talked about ideals. We defined them. We said if 0 is an element of this set of polynomials, and 2 polynomials being in the set means that their sum is in the set, and then taking any polynomial in that set and multiplying by a generic polynomial in the larger ring gives you a polynomial in that set. If that happens, what you're looking at is an ideal. That's how we define an ideal. It's very abstract, and it's not 100% clear what that means when you just look at this definition. And then we looked at a concrete example. We said, let's look at the ideal generated by polynomials f sub 1 through f sub s. And we defined it this way. You take the polynomials, you multiply by polynomials in our ring, add them together, and it turns out that that is an ideal generated by s polynomials. And then we proved it was an ideal, just going through those 3 requirements for an ideal. But that wasn't particularly insightful. For me, the excitement comes from here, this interpretation of what this ideal is. Because this very abstract object is meaningful. This is telling us that if we have s polynomials in n unknowns, x sub 1 through x sub n, well, that list of s polynomials, each of those could be set equal to 0. And now we've got a system of s polynomial equations and s unknowns. Well, we can take those polynomials, we can multiply them by other polynomials, we can add them together, and then we get a consequence of this system of equations being true. Since all of these are set equal to 0, when we multiply all of these equations by polynomials and add them together, the sum is also equal to 0. So if we think of these polynomials as being the defining feature of this system of polynomials, the system of polynomial equations, this polynomial equation is a generic consequence of all of these polynomial equations. And when I say generic consequence, I mean it's every possible consequence of this system of polynomial equations. Now, we have infinitely many consequences, but we usually like to follow an algorithm to try to get rid of one of the variables, rid of one variable at a time to find the value of one variable and then back substitute. We're going to do something similar here, but they're not, these systems of polynomial equations aren't nearly as easy to solve as systems of linear equations like the ones you studied in linear algebra. But we've got the ideal generated by these polynomial functions, f sub 1 through f sub s. And basically what that is it's a set of polynomials consisting of all polynomials that would equal 0 if this system of equations defined by the original functions f sub 1 through f sub s were equal to 0. So our textbook author calls this set of all polynomial consequences of the original system of equations. Think of it as polynomial, when he says polynomial consequences, think set of polynomials. If you're saying, well, polynomials aren't equations, you're right. If we take those polynomials that we started with and set them equal to 0, and we take these equations and multiply them by other polynomials and add them together, that's giving us a new system of equations. It's giving us infinitely many equations that you would get, infinitely many consequential equations, equations that would be consequences of this system of equations being true. The ideal consists of all of those polynomials that would be 0 if this system of equations is true. And then remember what an affine variety is. An affine variety, defined by functions f sub 1 through f sub s, is just a solution set of a system of equations. So this is a subset of n-dimensional space. if you graph it, it's a set of points or a curve or a surface or a hypersurface or something like that, but it's a subset of n-dimensional space where all of these equations are true. The ideal is not a subset of space, it's a set of polynomials, all of which would be equal to 0 because those are 0. And this ideal is going to be closely related to this affine variety. Okay, so we talked about the ideal generated by f sub 1 through f sub s, and then we looked at an example from the exercises. And we worked it out. And we said, now we've got a polynomial ring defined by these two polynomial functions. It's the set of all polynomials of this form. And one of the polynomial consequences of these equations is this one, that x to the fourth minus x squared plus 1 is 0 when this is 0 and that is 0. Okay, so we're going to keep going just a little bit longer, just a couple more facts, and then we'll wrap up this video. This is just a term. We say that an ideal given by I is finitely generated. If there exist, that's what that backwards E means, polynomials f sub 1 through f sub s in our polynomial ring in n variables with coefficients in the field k, such that I is the ideal generated by those s polynomials. Now, we're not going to prove this here. We're going to prove this later. This is a fact. It's called the Hilbert basis theorem. The Hilbert basis theorem says this: every ideal of the polynomial ring in n variables with field coefficients in the field k is finitely generated. That's powerful. So that's saying that if there is an ideal that satisfies those three properties, it contains 0. If two polynomials are in the set, the sum is in the set. If you take any old polynomial from the larger ring and you multiply it by an element of the set, you're still in the set. All of those are generated by a finite number of polynomials, f sub 1 through f sub s. S is a finite number. Now, if we have an ideal and it's finitely generated so that this ideal is generated by the functions f sub 1 through f sub s, the polynomial functions f sub 1 through f sub s are called the basis of I. So it's kind of like basis vectors, but not exactly. We say that this is a basis, the set of polynomials f sub 1 through f sub s is a basis of I. And we should note that a basis is not unique. A given ideal may have many different bases. Now, on the surface, you might think, why would an ideal have infinitely many, or why would a given ideal have, or potentially have many different bases? Well, think about what we were just talking about before. Like, I could use this system here of two linear equations and two unknowns as the basis, or I can multiply this one by 2. I could use that or I could, well, let me say that differently. If I subtract the 3 from both sides, the function f1 equals 2x plus 4y combined with the function f2 equals negative x plus 5y minus 3. F1 and F2 could be the basis of an ideal generated by this function and this function. But rather than using those two, I could multiply this second one by 2 and subtract the 6 from both sides, and that could form a basis for the ideal generated by those two. Now, this one guy is not going to form the basis. But there are infinitely many ways that we could have two linear equations and two unknowns that would give us the same solution. So all of those would be different ways to represent that ideal. So just think about that for a bit. It makes sense that a given ideal might have different bases. Because the system of equations that's describing like all of those consequences of the original polynomials, I mean, that system is not unique. You can take a set of polynomials and then transform them into another set of polynomials, and it could potentially still define exactly the same ideal, the same set of polynomial consequences as the original polynomials that you started with. So hopefully, with that in mind, this idea isn't too surprising. And if it is surprising, you should think about it a little bit more and think about like why that makes sense. To me, it makes a lot of sense. Okay. Now, one other thing that we'll talk about before we go on is this proposition. It says, let's say that f sub 1 through f sub s and g sub 1 through g sub t. These are both sets of polynomial functions in our polynomial ring with coefficients in k and variables x sub 1 through x sub n. So if both of these are bases of the same ideal, in our polynomial ring, then the affine variety defined by the first set of polynomials is equal to the affine variety defined by the second set of polynomials. Now, I'm not going to prove this, but again, I think that our intuition tells us that this must be true. If this is giving me one set of polynomial consequences, and this is getting me a different set of polynomial consequences, in much the same way that I can take these equations and multiply them by something and get a new system of two equations and two unknowns. Or like we did up here, we could take these equations and multiply them by x squared and another function, and then add them together and you get another equation. There are lots and lots of different ways we can do that. But if we have these s equations and they all have the same polynomial consequences as these t equations do, or when I set these polynomials equal to 0, I have those s equations. When I set these polynomials equal to 0, I've got those t equations. If both of those are bases of the same ideal, so basically like a manipulated version of the system of equations that you started with over here, or the system of equations that resulted from the polynomials that you started with over here. The solution set of those systems of equations is going to be identical to each other. If this ideal is equal to this ideal, and that's what we're saying here, these are both bases for the same ideal, then their affine varieties are the same. So what this is saying is a very important fact. Affine varieties are not determined by polynomial equations. Affine varieties are determined by ideals. So it's not the particular basis functions that you use that is important. It's the consequences of those basis functions. Remember how that works with all of the consequences. We're taking all of these guys, we're multiplying them by generic polynomials, any polynomials we want, we're adding them together and we're getting a polynomial consequence, which is just h1 f1 plus h2 f2 plus h sub s f sub s. All of those have to equal 0. But we're talking about all of the consequences of this system of equations being true. The affine variety is determined by that, all of those consequences, not the particular polynomials that you're starting with. Now, you probably already know that this is true based on your intuition, based on what you know about solving nonlinear systems of equations. If you've taken pre-calculus, you've done something like this before. Here's an example from the book. I think it's a great example. We have an affine variety defined by these two polynomial functions, 2x squared plus 3y squared minus 11 and x squared minus y squared minus 3. So those are polynomials in two-dimensional space. I'm going to assume that x and y are real numbers and that our field is the field of real numbers. So this is the set of all ordered pairs in the plane such that this equation is true and this equation is true. If I add 11 to both sides, I get that. And if I subtract or add 3 to both sides, I get that. So both of these equations are true at the same time. Well, I could stick with these two equations to define this variety, but most of the time, if you're trying to figure out the solution set of this system of two equations and two unknowns, you're going to replace this system of equations with a simpler system of equations. Right now, this is our first basis. I've got this is my F1 and this is my F2. Let's find G1 and G2 so that when I have G1 and G2 here, these equations should be, the G1 equation and the G2 equation should be much, much simpler than these two equations right here. And it's actually pretty simple to make that happen, just using pre-calculus techniques. So I've got this here. And let's say I want to get rid of, say I just want to get rid of y. So let's multiply this equation by 3 and then add them together. Then I'll have 5x squared equals 9 plus 11, which is 20. So you have x squared equals 4. Or if you prefer, so that it looks more like a polynomial set equal to 0, x squared minus 4 equals 0. So that's one consequence of this system. Now another consequence of this system might come from taking the second equation, and rather than multiplying it by 3 and adding them together, I might take the second equation and multiply it by -2 and then add them together. Again, it's just pre-calculus, guys. There's nothing fancy here. The abstract math, a little fancy. When I multiply these equations by, or the second equation by -2, when I add them together, I get 5y squared equals I've got 6 plus 11, which is 17. Did I do that right? It's multiplying the second equation by -2. There we go. 11 minus 6 is 5. So if we divide both sides by 5, we get y squared equals 1. So y squared equals 1 was one consequence of this system. We had x squared equals 4 was another consequence of this system. Or if you prefer, you can write it this way: x squared minus 4 equals 0, and y squared minus 1 equals 0. Or you can even go further and say that x equals plus or minus 2 and y equals plus or minus 1. Now, this is not an affine. Well, actually, I was going to say that's not an affine variety, but maybe it is. We have x equals 2, x equals -2, y equals 1, y equals -1. So we could write this way: x minus 2 equals 0, x plus 2 equals 0, y minus 1 equals 0, y plus 1 equals 0. But the original variety that we started with looked like this. We know it was a system, or a system of two equations and two unknowns. We're looking for ordered pairs in the xy plane such that this is 0 and this is 0. That turned out to be equal to this affine variety. And this affine variety is much more insightful. From this, I can see that x must be plus or minus 2 and y must be plus or minus 1. And then we could also write it in terms of that variety. It's kind of an interesting choice. We've got 4 equations and 2 unknowns. But this is equal to this, which is equal to this. Now, which one of these looks simpler to you? I mean, I think this one's the simplest looking. This one's most intuitive, I think. And this is least intuitive, but at least we know what it tells us to do. It says that this affine variety V is a set of all points in the xy plane such that this is true and this is true. And so what we get is x equals 2, y equals 1, x equals 2, y equals -1, x equals -2, y equals 1, x equals -2, y equals -1. And that's it. We get 4 ordered pairs. So we get 4 ordered pairs is the solution, or is this affine variety, which is this affine variety, which is this affine variety. And I want you to see that what we've done here with the ideal is we've changed the bases. So this affine variety, which consists of these 4 points, it was defined in terms of a number of bases. So here's our first basis. You take this equation set equal to 0, and you take this equation set equal to 0. You multiply them by polynomials, add them together, and that's every possible polynomial consequence of the fact that both of these are equal to 0, and you get these new polynomials that are also 0. Or we could write it like this. Or we could write it like this. And all 3 of those are ideals that represent the same set. So we've got 2 basis vectors here, I said basis vectors. I've got 2 polynomials in my basis for the ideal here. I have 2 polynomials in my basis here. I've got 4 polynomials here. And any one of those would work as the ideal associated with this particular affine variety, which consists of this set of 4 ordered pairs. So let's go back to proposition 4 and what it says. It says that if 2 sets of polynomials are bases of the same ideal, then the corresponding varieties are equal. Even though that's very abstract in the way it's worded, remember what that means. Like, this is just a system of equations, and this is a system, or this corresponds to a system of polynomial equations, and this corresponds to a system of polynomial equations when we set all those polynomials equal to 0. what we're saying is it doesn't matter which form of the system you are starting with if both of those form the same basis or form a basis for the same ideal. The solution sets of those systems of equations are going to be identical to each other. Just like the solution set of this system of equations and this system of equations and this system of equations are all this set of 4 ordered pairs. Okay, so that is the end of our initial discussion of ideals and their relation to affine varieties. If 0 is in the set, if f and g are in the set, f plus g is in the set, if h is a polynomial and f is in the set, h times f is in the set, that's what makes an ideal an ideal. We can create an ideal by taking a bunch of polynomials, multiplying them by their polynomials and adding them together. That turns out to be an ideal. And our interpretation of this is an ideal is the set of all polynomial consequences of the system of polynomials given by f sub 1 through f sub s being all equal to 0. So you take these guys, you multiply by any generic polynomial, add them together, and you're going to get another member of the ideal. So this is a set of polynomials. The ideal is a set of polynomials, all of which would equal 0 because f sub 1 through f sub s are all equal to 0 at the same time. Now the Hilbert basis theorem just says that every ideal is finitely generated by some number of polynomials f sub 1 through f sub s. There's no ideal out there where you need infinitely many of them. You're going to get to stop at some point. Someday you're going to have 100 polynomials and you're going to say that's enough. That's enough to generate the ideal. Totally fine. We have not proven that yet. We're going to build toward proving that. But that's a really important fact that every ideal can be written in terms of an ideal generated by a finite number of polynomials. And then the last thing we did not prove, but we discussed, was that affine varieties are determined by ideals, not equations. So affine varieties are solution sets of systems of polynomial equations. What proposition 4 says is that solution set is really not about the functions that you started with that defined that affine variety. It's about all of the consequences of those functions being equal to 0. It's determined by the ideal generated by those functions and not the equations themselves, because you could use the equations themselves to come up with infinitely many other equations. As long as you're generating the same set of consequences, you would get the same affine variety. So it's really about the ideal and not the particular equations on your list. As we see, when I use these equations, or these equations, or rather, these equations, or these equations, or these equations, these are polynomials, right? They become equations when we set them equal to 0. Any one of those versions is giving me exactly the same affine variety. So generally we want to go to the simplest one because that's going to tell us what our solution set looks like.